Good afternoon, everyone. Thank you for joining us for the What Works Clearinghouse webinar. Today's webinar will focus on the effect size in standard error formulas that are new to the version 4.1 of the WWC standards. My name is Natalia Gnetko-Berry. I'm a senior researcher at American Institute for Research, where I support the training task for the WWC Statistics website and training contract. On behalf of the Institute of Education Sciences and the WWC, I welcome you to today's webinar. Two experts will lead the webinar today, Dr. David Miller and Dr. Ryan Williams. Doctors Miller and Williams are research methodologists with considerable expertise in quantitative research. They're also leading contributors for the WWC Statistics website and training contract at AIR. Now, before we begin, I would like to address one question that we usually receive around this time. Will the slides be available? Yes, the recording of this webinar and the slides will be available. Please submit your additional questions through the chat box. And near the end of the webinar, presenters will answer questions. We'll provide all questions and answers, including those we are and are not able to discuss today, in the archived webinar materials, which will be posted to the WWC website along with the slides. Throughout the webinar, we will be sharing links to resources in the chat box, so you may want to keep the chat box visible on your screen. Now, what do we want to cover in this webinar? Our goal is that after the webinar, you understand the importance of the new effect size and standard error formulas for version 4.1 of the WWC procedures, that you learn the most frequently used formulas, understand the importance of covariate adjustment in standard error calculations, and that you understand options for clustering adjustment. And toward the end of the webinar, we also plan to walk you through how to use the online study review guide to implement these new formulas. So with that, I'll turn the webinar to our first presenter, Ryan.
Thanks, Natalia, and thank you all for joining. In this first part of the presentation, we're going to discuss the importance of effect sizes and standard errors in the What Works Clearinghouse. Specifically, why they matter for the recently adopted fixed effects meta-analytic approach, their role in computing p-values, and why we have an ongoing task of expanding the toolbox of effect size and variance estimation procedures. With the introduction of the 4.1 handbooks, the WWC formally adopted a meta-analytic framework for effect size synthesis. In the past, study findings from intervention reports specifically were combined using a simple unweighted average. And the evidence rating was based on the number of individual findings that were statistically significant. For example, under version 4.0 and earlier, an intervention could receive the highest evidence rating if at least 2 studies showed a positive and statistically significant result. No studies showed statistically significant or substantively important negative results, and at least one of the findings met standards without reservations. This is a form of vote counting, which has a number of well-documented limitations in the literature. In the version 4.1 handbooks, the WWC transitioned to what is known as a fixed effects meta-analytic framework. Within this framework, study effect sizes are assigned weights that are inversely proportional to their variances, or standard errors, which are largely a function of study sample size. For example, if 2 studies met WWC standards with or without reservations, and of those studies, one had a total sample size of 10 individuals, and the other had a total sample size of 350 individuals, the larger study would contribute more to the fixed effects meta-analytic average than the smaller study, which is to say the meta-analytic average would be closer to the effect from that larger study than the smaller study. In cases where the study samples are similar, the contribution to the meta-analytic average will be more evenly distributed among them. Because of this transition to a fixed effects meta-analytic framework, the WWC review process needs to include procedures for extracting effect size standard errors to calculate those meta-analytic weights. The version 4.1 Procedures Handbook provides effect size standard error formulas for many of the combinations of designs and outcomes that WWC reviewers will typically encounter. The version 4.1 supplement provides a number of extensions to those formulas in hopes of accommodating more complex designs that reviewers may eventually encounter. This is all part of our ongoing work to expand the toolbox of effect size and standard error estimation procedures. And this work helps ensure that more studies that otherwise satisfy the WWC design standards can contribute to intervention effect summaries. Additionally, part of this ongoing work to expand the toolbox is to identify optimally efficient effect size and standard error estimation procedures so as to close the gap between the findings from the WWC review process and the findings from a primary study. For example, many primary study researchers who use cluster level assignment designs adjust for covariates such as pretest in their impact analyses. Until this supplement was released, the WWC did not have a method to account for the precision gains from those kinds of adjustment strategies. In the following few sections, we're going to describe how the WWC will approach that issue and others as laid out in the version 4.1 supplement. In the next section, David will discuss the 4.1 supplement content that is relevant to individual level assignment studies.
Thanks, Ryan. We will first present effect size and standard error formulas for the individual level assignment studies, such as when individual students are randomly assigned to conditions. We will start by first discussing the simplest formulas based on unadjusted group comparisons. Then we will describe options for covariate adjusted group comparisons, especially focusing on a new approach for regression adjusted standard errors that was recently introduced 2 months ago with the publication of the version 4.1 supplement to the WWC Procedures Handbook. The WWC uses the Hedges-G effect size as a standardized measure of intervention effect. This metric represents the mean difference between intervention and comparison groups on a standard deviation scale, enabling comparison across outcome measures and aggregation across studies. For instance, in this graphic, the standardized effect size would be the distance between the peaks of the two distributions divided by the width of those distributions. The width is defined here as the standard deviation within these groups. To illustrate how to compute the Hedges-G effect size, we will use an example study in which individual students were randomly assigned to receive business as usual instruction or a mathematics intervention called Focus Math. This table shows the unadjusted means and standard deviations separately for the intervention and comparison groups, both at baseline and at a mid-year outcome time point. For simplicity, we will first focus on only the unadjusted outcome statistics shown on the right-hand side of the table, temporarily ignoring the baseline statistics shown on the left-hand side of the table. This slide shows how to map the table's information to mathematical symbols we will use in the following slide. The letter N corresponds to sample sizes, Y corresponds to outcome means, S corresponds to standard deviations, and the subscripts I and C respectively correspond to the intervention and comparison groups. Here are 4 steps for computing the Hedges G effect size using unadjusted means and standard deviations for individual level assignment studies. First, compute the unstandardized difference in the raw intervention and comparison group means. Then, divide that difference by the pooled standard deviation, which you can think of as a type of a weighted average between the intervention and comparison group standard deviations. Then, compute the small sample bias correction term omega, which is usually slightly less than 1, resulting in small downward adjustments to the effect size. Though typically small, this adjustment is needed to yield approximately unbiased estimate of the population effect size. The term DF corresponds to the degrees of freedom, which in this case is the total sample size minus 2. Then we combine these steps to yield the effect size as shown in the last equation for step 4. We can apply these formulas to the earlier study example. The raw mean difference of 1.28 is converted into a standardized mean difference of 0.09. In other words, the intervention group outperformed the comparison group by 0.09 standard deviations. Please note that for all numeric calculations in this webinar, computed values are rounded to 2 decimal places for presentation purposes only. To reproduce later calculations, audience members would need to use the full unrounded values from these intermediate calculations. Next, we seek to understand the uncertainty in this 0.09 effect size estimate by computing its standard error. Smaller standard errors indicate more precise estimates, such as when using larger sample sizes. The standard error formula shown here is applicable to unadjusted comparisons of continuous outcomes in many scenarios, even including Hedges G values computed using test statistics such as F-values from analysis of variance or ANOVA models. The left-hand part of this formula is usually a much larger contributor to the overall standard error and represents uncertainty introduced by the raw sample mean difference. The right-hand part represents the uncertainty introduced by dividing that raw difference by another sample statistic, which is the pooled standard deviation. This formula appears in Appendix E of the version 4.1 WWC Procedures Handbook. We can apply the standard error formula to this study example, yielding a standard error of approximately 0.11. We can also use the standard error to compute the WWC calculated p-value for this finding. We divide the effect size by the standard error to yield the t-test ratio. Then we obtain the p-value based on the t-distribution with n-2 degrees of freedom, yielding a p-value of 0.42 in this case, which is not statistically significant. We can compare these WWC calculations to the study-reported analyses, finding that they greatly diverge in terms of the p-value. The authors reported a p-value of 0.03, which is statistically significant, yielding qualitatively different conclusions than the WWC calculations presented so far. Interestingly, however, the computed effect sizes match, as shown in the top row. So, what is going on here? Were the authors' calculations incorrect, or were the WWCs? It turns out the answer is neither. The difference is in how these two sets of calculations accounted for baseline covariates. The WWC calculations presented so far were based on unadjusted comparisons without baseline covariate adjustment, whereas the author's analyses controlled for a wide set of baseline covariates, such as baseline achievement, baseline self-efficacy, student demographics, teacher characteristics, and school fixed effects. Controlling for baseline covariates, as the study authors did, is favorable by increasing statistical precision, reducing the standard error. It can also help reduce bias and estimated mean differences, such as in quasi-experimental designs. Lastly, it helps satisfy certain WWC baseline equivalence requirements. The WWC allows for several acceptable adjustment options, such as multiple regression, which is what the study authors did in this study example, analysis of covariance, or ANCOVA for short, and difference in differences adjustments. The WWC has long factored in these types of covariate adjustment options into its computation of effect sizes, including in the very first WWC standards version, version 1.0. However, the p-value calculations in these prior versions have not accounted for the precision gains and reductions in standard errors offered by covariate adjustment. As a result, the WWC calculated p-values can often diverge from those reported by the study authors, as WWC reviewers in today's audience can likely attest to. But now, the new version 4.1 Procedures Handbook and Supplement offer options to account for these precision gains in the effect size standard errors, representing advances in meta-analysis methodology. Consequently, the WWC's and authors' calculations will now also more closely match each other more often using sound statistical procedures, as we will illustrate in the following slides. This slide shows one example standard error formula that incorporates the precision gains offered by covariate adjustment in either multiple regression or ANCOVA models. The bottom formula incorporates the proportion variance explained, or R squared, into the left-hand side. Statistical models that explain more residual variation in the outcome will yield larger R squared values, reflecting increased precision in intervention effect estimates and generating smaller standard errors. This formula also appears in Appendix E of the version 4.1 WWC Procedures Handbook. Hence, model R-squared values help capture the increased precision from baseline covariate adjustment. But one problem is that studies often do not report R-squared values. Studies do, however, often report another critical piece of information about uncertainty, which is the regression coefficient standard error. For instance, this table shows how the example study reported information about the regression-adjusted estimate of the intervention effect. The unstandardized coefficient of 1.33 would be used for computing the covariate-adjusted effect size using consistent with established WWC precedent. Prior WWC versions, however, would ignore the regression coefficient standard error. With the new procedures supplement released 2 months ago in October, we can now use this critical piece of information about uncertainty and calculating the effect size standard error. This slide shows how to compute the effect size using the regression coefficient. All the steps are the same as before, except for the first step, where the raw mean difference is replaced with the unstandardized regression coefficient, representing the covariate adjusted mean difference. The computed effect size remained roughly the same, yielding 0.09 standard deviations. Next, we will use the standard error for the regression coefficient to compute the standard error for the effect size. The regression coefficient standard error is 0.61. It seems intuitive that we could simply standardize this 0.61 value by dividing it by the pooled standard deviation in the same way that we standardize the coefficient value of 1.33. This intuition gets us close to the desired formula, but it would ignore the uncertainty introduced by using the sample standard deviation as the standardizer. Nevertheless, the standard error formula on the next slide builds on this intuition. Here's that formula. The left-hand side represents the intuitive idea that we can simply standardize the regression coefficient standard error by dividing it by the pooled standard deviation. We still need to include the right-hand term to incorporate the uncertainty introduced by dividing by the pooled standard deviation in the effect size computation. Notice that this right-hand term remains the same as compared to the earlier standard error formulas. Notably, this formula accounts for the increased precision with covariate adjustment and can even accommodate more complex regression models, such as multiple imputation. The derivation of this formula was based on the delta method, which is a commonly used and flexible approach for deriving analytic standard error formulas. To use this formula, the study must report three key pieces of information: the unstandardized regression coefficient, its standard error, and the unadjusted within-group standard deviation. The example study reported this information, so we can apply the formula, along with comparing it to the prior unadjusted approach and the author's analyses. We see that the computed effect sizes all closely match each other, but the two WWC approaches yield substantially different standard errors. The regression-adjusted standard error approach yields a standard error that is 61% smaller than the unadjusted comparison approach. The regression-adjusted standard error approach should be favored here because it accounts for the precision gains with covariate adjustment, bringing the WWC calculated p-value in line with the author-reported value. Furthermore, this study will now carry more meta-analytic weight in cross-study syntheses compared to using the unadjusted comparison standard error formula. Here's a compilation of the standard error formulas presented so far for individual level assignment studies. Notably, all these formulas assume continuous outcomes, but the WWC Procedures Handbook and Supplement also provide formulas for dichotomous outcomes, as well as for difference in differences adjustments. Ryan will cover next the extensions for cluster level assignment studies.
Thanks, David. In this next section, I'm going to walk us through the process for calculating effect sizes for cluster level assignment studies using similar steps to the ones that David just described for individual level assignment studies. Then I will present a method for adjusting cluster level assignment effect size standard errors for covariates that may have been used in a primary study's impact analysis. We'll finish with an overview of some of the additional cluster level assignment standard error extensions that are in the 4.1 supplement. The 4 steps for computing effect sizes from cluster level assignment studies follow the same 4 steps used in individual level assignment studies, starting with the computation of the difference in treatment and comparison group means, which is B, computing the pooled within group standard deviation, S, computing the small sample correction, omega, and putting all of those pieces together to generate a Hedges G effect size estimate. In fact, the only differences between the procedures used for cluster level assignment studies are in the small sample correction and an additional adjustment used in the final computation of Hedges G, which ensures consistent estimation of the population effect size in the presence of clustering. The first distinction we see is in the small sample adjustment formula. In cluster level assignment designs, the degrees of freedom term, H, has a different and considerably more complicated form. The new pieces of information that go into computing H include the average cluster size, little n, and the intraclass correlation, denoted as rho subscript ICC. The intraclass correlation is the most consequential piece of information related to cluster level assignment studies. It indicates how correlated individual level outcomes are within clusters. Values range from 0 to 1, with 0 indicating the outcomes are fully independent, that is, no clustering, and values of 1 indicating full clustering, that is, outcomes that are exactly equal within clusters. The WWC uses a default value of 0.20 for academic achievement outcomes and a default value of 0.10 for all other outcomes when the intraclass correlation is not reported in the primary study. With the total individual sample sizes, those pieces of information allow us to generate H, and therefore the small sample correction needed for Hedges G. The second distinction is in the final computation of Hedges G, where the products of the 3 earlier steps are brought together. An additional correction, which we call the small number of clusters correction, denoted as gamma in the 4.1 supplement, is needed in this final step. This correction ensures that the Hedges G effect size from the cluster level assignment study is a consistent estimate of a population effect size in the presence of clustering. Gamma has a maximum value of 1, and in many, if not most instances in the WWC review process, it will be very close to 1, indicating a small bias correction. Note that when the intraclass correlation is 0, each of these steps reduce to the steps used to compute effect sizes from individual level assignment studies. Now we're going to discuss the methods in the 4.1 supplement that were developed to address an important issue: how to adjust effect size standard errors for covariates in cluster level assignment studies. Often, researchers and evaluators will design and power their cluster level experiments with the anticipation of using covariates such as pretest measures to increase the precision of their impact estimates. These kinds of covariates can matter a lot for estimate precision, and ignoring them in the WWC review process can lead to an inconsistent conclusion about an intervention's effect. For example, a primary study may control for a pretest measure and demographic covariates, and they may observe a positive and statistically significant impact estimate. But if the WWC were to estimate an effect size and standard standard error, ignoring the outcome variance explained by those covariates, it may not determine the effect to be statistically significant. So that's one reason we developed methods for making these kinds of adjustments in the review process, hopefully closing the gap between the conclusions from the WWC review process and the conclusions in the primary studies. The other reason these additional methods are important for the 4.1 supplement is because of meta-analysis. Ignoring variance explained by pre-intervention covariates can have a substantial impact on the effect size weights, where ignoring them leads to larger variances and diminished contribution to the meta-analytic average, which is used to characterize the level of evidence for an intervention. I'm now going to walk us through an example from Rutherford et al. 2014. This was a cluster randomized experiment of an elementary school math program. I've pulled out some copies of the text and tables from the publication to illustrate how we would navigate this part of the review process. The first step is calculating the effect size, using the same 4 steps we discussed earlier. Note, I am going to focus on estimating an effect size for the pooled effect, but we'd use the same steps to compute an effect size for any of the other groups, such as individual cohorts or grade-specific effects. Keep in mind that while I'm walking us through this process manually, if you are a WWC reviewer, these are automated within the online study review guide. Hopefully, though, this gives you some additional insight into what the OSRG is doing on the back end. And if you're conducting your own review and meta-analysis, this should give you a sense of how you would approach the application on your own. So step 1, extract the information needed for the effect size numerator, B. In this case, we have a covariate adjusted mean difference, which is 5.12, as presented in table 3 from the primary study. Step 2, compute the pooled within group standard deviation F. To do this, we go to table 2 and extract the standard deviations for the treatment and control groups, as well as their sample sizes. We plug those into our formula for F, and we get a pooled standard deviation of 78.22. Step 3, compute the small sample correction. First, we need to calculate the degrees of freedom term, H. This is probably the most complicated formula because it has so many terms. Notice that I added a bit of text from the publication that we needed to compute our average cluster size, little n, which is just the total individual sample sizes divided by the number of clusters, which is 52 in this case. That leads to a value of about 265.44. I've also pulled in the WWC default value of 0.20 as our ICC for this study. If we plug all of that information into our formula for H, we get our degrees of freedom, which are about 1,217.93. And with that, we can then get our small sample correction omega, which is about 1.0 after rounding. Because this is a fairly large study, large n, large big N, large little n, the small sample correction is extremely small. Step 4, we bring all of the pieces together and compute Hedges G, and we multiply by our small number of clusters correction, which turns out to be about 0.99. This leads to a final Hedges G estimate of 0.07 standard deviations, which is consistent with the study reported effect size, which is also 0.07 standard deviations. The next part is the really important part, computing the effect size standard error, adjusting for model covariates. Rutherford et al. Adjusted for a math pretest, as well as a pre-intervention English measure and some grade fixed effects. We're going to use equation E.5.2 from the 4.1 procedures handbook, which ignores covariates, Then we will use equation E.7.0 from the 4.1 supplement to demonstrate how consequential accounting for covariates in cluster level assignment studies can be. Here are the two formulas. The two formulas are very similar, differing only in the left-hand terms within the radicals. But the one that ignores clustering, E.5.2, has a term eta that represents the design effect, which is 1 plus little n minus 1 times the intraclass correlation. The E.7.0 formula uses the same gamma term we defined earlier, as well as the cluster-corrected standard error, which we term SE subscript CC, which would come from something like a hierarchical linear model or an ordinary least squares regression with cluster-robust standard errors. The other term in E.7.0 is S, which is the pooled within group standard deviation that we saw earlier. And both formulas have G squared divided by 2 times H, where H is the degrees of freedom term that we saw earlier as well. So let's first plug in the values needed to generate a standard error for the Rutherford et al. 2014 example, ignoring covariates. We first compute our design effect using the WWC default ICC value for achievement outcomes, which is 0.20, and that ends up being about 53.88. Unlike the gamma and omega terms that we've seen and computed already, eta, or the design effect, will tend to be quite a bit larger than 1. We know omega is about 1.0. We know what our individual sample sizes are. We have our Hedges G effect size, and we know our degrees of freedom term H. Taken together, we can compute our cluster level assignment effect size standard error that ignores covariates, which is about 0.12. We'll now calculate the standard error accounting for covariates that were used in the Rutherford impact analysis. We go back to table 3 and we capture the standard error that corresponds to the pooled impact estimate, which is 2.97. Using that with the other pieces of information we already have, the small sample correction, the pooled standard deviation, the small number of clusters correction, the Hedges G effect size, and the degrees of freedom, we arrive at an estimated standard error of 0.04. Using this standard error that is adjusted for covariates leads to a statistical conclusion that is much more consistent with the statistical conclusions in the primary study. And adjusting the standard error for covariates in this example increases the study's potential contribution to a meta-analysis by a factor of about 9. Our example focused on a situation where the primary study authors properly adjusted for clustering in their impact analysis. That is, their standard errors were inflated proportional to the level of clustering in the study. In cases where the impact analysis is mismatched with the design, where clustering is not accounted for and it should be, equation E.7.1 provides an alternate estimation procedure where the naive covariate adjusted standard error is cluster corrected using the design effect eta. In addition to the covariate adjustment method for cluster level assignment studies, the version 4.1 supplement includes 5 other cluster level assignment study extensions. These include ANCOVA, gain score difference in differences, effect size difference in differences, with and without a study reported correlation, and models with dichotomous outcomes. In the next section, David is going to walk us through some practical guidance for WWC reviewers using the online study review guide.
Thanks, Ryan. I will talk next about how WWC reviewers can use the online study review guide, or OSRG for short, to implement the formulas presented today, covering how to choose between effect size computation options, entering statistical information in the version 4.1 OSRG, which will be released later this month, and understanding how the entered information affects back-end computations. The OSRG will automatically apply the formulas presented today based on study information that reviewers will enter, such as means and standard deviations. WWC reviewers will need to know how to correctly enter this study information and understand the consequences of selecting different menu options. But reviewers do not need to hand calculate the effect sizes and standard errors themselves. The OSRG will do that hard work for reviewers. Most of the version 4.1 changes affect only back-end calculations, but reviewers should still be aware of the expanded options, especially to account for the increased precision when controlling for baseline covariates. This screenshot shows a list of the menu options for effect size computation types. The OSRG user selection here will determine which pieces of statistical information the OSRG will use to compute WWC effect sizes and standard errors. OSRG users should be aware of three general principles when selecting the effect size computation type in that previously shown drop-down menu. First, users should generally prefer approaches based on covariate adjustment over those based on unadjusted comparisons. These covariate adjustment options will show up to OSRG users as ANCOVA adjusted post-intervention means, ANCOVA F-test and correlation, ordinary least squares regression, or OLS, and hierarchical linear modeling, or HLM, level 2 regression coefficient. Second, the lack of reported information is often constraining. For instance, unadjusted standard deviations must always be entered to compute effect sizes using regression coefficients. If those are unreported, other computation options may be required instead, such as those based on test statistics. Reviewers should consult with review team leadership as needed to make these decisions and recognize when author queries may be needed to gather the required information. Whenever possible, it is important to select an option that allows for computing effect sizes. Otherwise, without an effect size, the finding cannot contribute to the meta-analytic averages in cross-study syntheses. And the third principle is that reviewers should always select the dichotomous option for dichotomous outcomes, such as high school dropout or college graduation. Dichotomous outcomes require special formulas that do not apply to continuous outcomes. One example of version 4.1 OSRG changes concern the new regression coefficient formulas. This screenshot is from the current version 4.0 OSRG for the OLS regression coefficient computation type. Reviewers should enter values in the coefficient and standard deviation fields to allow the OSRG to compute the WWC calculated effect size. But notably, there is no input field for entering uncertainty information about the regression coefficient. These screenshots show three new added input fields to accommodate the new version 4.1 formulas. These fields are the coefficient standard error, coefficient test statistic, such as a t or z value, which the OSRG can use to infer the coefficient standard error. That conversion would happen automatically. And the proportion variance explained, or R-squared value. The new inputs provide improved ways of calculating the standard errors and p-values for WWC effect sizes, accounting for precision gains with covariate adjustment, and often making the WWC calculated p-values more closely aligned with the author-reported values. These new input fields therefore represent improvements, but it is worth noting that they are not required either. If they are unreported, meaning that the reviewer does not leave those entries blank, the OSRG will automatically apply WWC defaults, which are generally conservative, such as assuming an R-squared value of 0, assuming no improvement in precision. These defaults account for the practical reality of imperfect reporting in the primary study article. A second example of version 4.1 OSRG changes concern clustering corrections. The OSRG includes an input field to flag cluster-level assignment studies. In addition to this field, for certain computation types, WWC reviewers must also tell the OSRG how to interpret certain author-reported values for cluster-level assignment studies. If reviewers enter author-reported test statistics, such as T or F values, or author-reported regression coefficient standard errors, then the reviewers must also tell the OSRG if these values accounted for clustering or not. This screenshot shows an example for coefficient-based computation. The highlighted question tells the OSRG how to interpret the coefficient standard error and coefficient test statistics fields. This question was already asked before in the versions 4.1 OSRG, but now it has moved closer to the specific input field it directly applies to for the version 4.1 OSRG. This slide shows how reviewers' answers to the "Did the analysis account for clusters?" field will route the OSRG to using different standard error formulas. If the user answers yes, the OSRG will use the left-hand formula with the gamma correction term, which is usually very close to 1, creating minor adjustments. If the user answers no, however, more drastic corrections are needed. The OSRG will use the right-hand formula in that case with the eta design effect correction term, which can often be much larger than 1, creating substantial adjustments, accounting for the author-reported standard errors that are too small. Hence, it is very important that reviewers accurately answer this input field question. Study authors can account for clustering in multiple acceptable ways, including using hierarchical linear modeling or applying cluster-robust standard errors to ordinary least squares regression models. I will end by summarizing 3 practical tips for WWC reviewers using the OSRG. First, take advantage of options for entering covariate adjusted analyses, including the precision gains they offer when computing standard errors and p-values. Second, be aware of how the chosen effect size computation type changes what pieces of information the OSRG will use in its back-end calculations. Third, record whether the author reported test statistics and regression coefficient standard errors accounted for clustering or not in cluster-level assignment studies. A webinar slated for January 2021, 1 month from now, will cover these points and other changes to the version 4.1 OSRG in more depth.
Well, thank you, David and Ryan, for walking us through this material. We're going to go to questions now, but before we do that, I would like to emphasize what Ryan and David have already said, that this information is available in a supplement to the WWC Procedures Handbook. You can find it on the WWC website. And we are going to post the link for you one more time in the chat box. That link should be coming up soon. So now let's go to questions. And the first question, David, I wonder if you can take this one. Can the regression-adjusted standard error approach accommodate multiple imputations?
Yes, it can. The regression-adjusted standard error approach can accommodate multiple imputations, provided that the author's reported coefficient standard error properly adjusts for the uncertainty from that imputation process. The version 4.1 WWC Standards Handbook, according to that Standards Handbook, the calculation of the reported coefficient standard error when using multiple imputation must meet two requirements. It must be based on at least 5 sets of imputations, and the calculation of the standard error must account for both the within imputation and between imputation variance components, as well as the number of imputations. Most established multiple imputation routines satisfy these requirements, but they are needed to be used for WWC purposes. In addition, if the analysis imputed outcome data for a cluster-level assignment study, the study must also provide evidence that the approach appropriately adjusted the standard errors for clustering by citing a peer-reviewed journal article or textbook that describes the procedures and demonstrates their effectiveness in accounting for clustering.
Thank you, David. Next question. How would you approach a situation in which the authors of a study reported an effect size, but it could not be replicated using the information in the study? For example, the WWC could calculate an effect size based on other information provided in the study, but it could be different from the author-reported effect size, depending on a number of possible factors. Ryan, can you address this question, please?
Sure. So the WWC generally reports the WWC calculated effect sizes because its computation can be verified and it supports comparability across outcomes and studies. However, in some cases, the WWC will use the study reported effect size if all of the following conditions are true. First, the study calculated effect size the effect size consistent with a WWC formula for Hedges G, including a small sample adjustment for continuous outcomes. Second, the study reported effect size regression adjusts for baseline differences, and the WWC calculated effect size does not or cannot, or the WWC calculated effect size is based on a post hoc difference in difference type of adjustment. Finally, when appropriate for dichotomous outcomes, the study used the Cox index to generate an effect size. And regardless of whether the WWC uses the author-reported effect size, it collects and reports this information in the data from individual studies database.
Thanks, Ryan. Our next question is about p-values. will the new methods be used to override study-reported p-values? David, can you walk us through that, please?
Sure. So the principles for selecting WWC calculated versus study-reported p-values in version 4.1 will remain the same as in version 4.0. So these principles state that in contrast to the study-reported effect size, the WWC generally accepts the study-reported p-values and statistical significance. This guidance is noted in page 9 of the version 4.1 WWC Procedures Handbook. However, and this is important, that there are two common circumstances in which the WWC calculated p-value will be favored over the study-reported p-value. The first circumstance is the study does not include statistical significance estimates, or there is a known problem with the study calculations as determined by review team leadership. And the second circumstance is the statistical significance levels reported in the study do not account for clustering when there is a mismatch between the unit of assignment and unit of analysis, as in cluster level assignment studies.
Thanks, David. Our next question has been discussed already in the chat box, but in case some of the members of our audience missed it, let's answer it verbally too. Why does the WWC use fixed effects and not random effects model for the synthesis of findings from different studies? Ryan, can you take this question, please?
Yes, I can. Yeah, it's a really good question. And the answer is doing a random effects model, implementing a random effects model requires estimating a between studies variance component. And that estimate can be pretty unreliable when the meta-analysis includes only a few studies, which is pretty common in most of the WWC intervention report syntheses. The fixed effects, plural here, the fixed effects model, on the other hand, allows the WWC to conceptually acknowledge variability in the effects. That is, there isn't maybe a true common effect, but that the observed effects and their variability are representative of that larger population of effects. And finally, the fixed effects meta-analysis offers a more robust approach to synthesis than the previous vote counting approach.
Thanks, Ryan. I think we can quickly answer one more question that we received earlier. I am a study author concerned with getting the highest WWC rating. Do I need to use these formulas to achieve the highest rating? David?
The answer is no. Study authors do not have to use the statistical formulas from the version 4.1 WWC procedures to achieve the highest rating. Authors should, however, be mindful to report all the needed information to apply these formulas. For example, if the study authors used multiple regression to estimate an intervention effect, they should, at a minimum, report the following: the unstandardized coefficient for the intervention effect estimate, the coefficient standard error, and the raw unadjusted standard deviation separately by the intervention comparison groups. And so the coefficient standard error is not required to compute WWC effect sizes or standard errors, but reporting it helps ensure that the WWC calculations align with the author's values. And providing effect sizes in study reports should be considered good statistical practice, but the WWC will verify these effect size computations using other reported information regardless.
Thank you, David. Thank you, Ryan. We will have to conclude for today. Before we go, one quick note is that you can sign up to receive notices from IES about additional webinars, and we're going to be posting a link for you. How to sign up, look it up in the chat box. If you have any additional questions after we close, please email these questions to the help desk. And with that, I thank you again for joining us today and hope that you will be joining us again soon.